Let's now, talk about, now that once the neural networks and, decision trees, so both nonlinear models have been discussed. Let's now talk about one of the very fundamental method, okay, proposed by Vapnik long time back, okay, and in fact, when he proposed that, not many people paid attention, right? It is only when after almost a decade later, people realize the strength of the method, okay, in solving problems, okay. And the method is known as the support vector machine. Okay, so what is a support vector machine, and why do we need it? See, typically, if you recall, in the introduction to machine learning lectures, where we were just discussing a very simple sample machine learning problem, right? Classifying data belonging to two different classes. We kind of showed that there could be a separating hyperplane, right? And we assume that the data is linearly separable, right? Okay, and there is a reasonable distance between the separating hyperplane and the different data points belonging to different classes, right? That's an assumption. However, if I have data points like this, right, and then data points like this, don't you think the it's going to become a bit tricky just to rely on this line as the separating hyperplane, right? Because there could be noise as well, right? The fact that this line is aligned this way, and then this point is close enough to the line, and also this red stars, pluses are also close enough to the line, sort of cast doubt on the efficacy of the separating hyperplane being the only line which separates the two classes, right? This could as well be, the noise, because of the effect of noise, the one that you see as the green one could actually be the red one, and vice versa. Okay, all right. So one separating hyperplane may not be enough. So is there a better way? Okay, the better way is that, and this is something what Vapnik suggested, that look, instead of one line, okay, can we have, so instead of one vector, right, can we have two vectors, and the two vectors are sort of supporting each other. They provide a support mechanism, okay, they provide a support mechanism such that the lines, the two lines being parallel to each other, right, provide a support in such a way that in between the two lines there cannot be anything. Okay, whatever is in between, right, it cannot be classified. Okay, and so instead of data points being aligned on either side of a single hyperplane, now you will have data points belonging to two different classes to be positioned in two different sides of these support vectors. Okay, in a matter of fact, something like this, okay, such that, okay, so what's the advantage of having these support vectors? One obvious advantage, these are the support vectors, right? These guys and these guys, right? One of the advantages of having these support vectors is this particular area, or the width of this particular separation, right, gives you the additional layover room, in the sense that if I use just the one separating hyperplane, the green lines, it could become too close to the separating hyperplane, or the red pluses could become too close to the separating hyperplane, and we are never sure. But in this case, at least, even if the green line or the red pluses, they could come close, there is not a single separating hyperplane, there are two. Okay, so therefore you still have enough discrimination that you can maintain, right? Okay, and that would actually lead to better classification. Okay, so the width is sort of expected to give classification results. Okay, at a layman's level. But how do we do that? I mean, how do we kind of sort of, quantify all that? So the goal is this. Now, when we quantify the width, there are some conditions, right? And one of those conditions is that, the data points cannot lie here. Okay, all right. So you have to have conditions that data points cannot lie here, because this is sort of the width that needs to be maximized, right? So quantify the width. In other words, we try to maximize this. Okay, all right, subject to some conditions. Correct. Okay, all right. Now what happens if some data point is wrongly classified or wrongly placed here, something like this? What happens? What will you do? Right? I mean, what we have to do is that if this is wrongly placed here, we need to somehow push this guy to the other side, right? Okay. So push this guy to the other side. How do we do that? Okay. So there are some techniques and methods available in linear algebra, which is the reason we talked about, introduction to linear algebra when we started this course, right? Okay. So we would take help of, projections. Okay. So these are some of the tools that we are going to use. Okay. Now, so what really happens is, so this is, I mean, you realize that this is equivalent to an optimization problem. So most of the classification problems that we see, right, including neural networks, right, I mean actually boils down to an optimization problem. Optimization is actually at the heart of machine learning. Okay, so this is an optimization problem. Okay, and the question is whether this is a convex optimization problem or not. Because convex or concave optimization problems are easy to track, they are NP-complete problems. If the optimization problem is non-convex, non-concave, it is computationally intractable, right? I mean, there are no analytical methods that could handle this, right? Even computationally, this becomes hard to track. Then you have to come up with meta heuristics and stuff like that. Anyway, however, we are actually not going to talk about that. So let's kind of look at the problem, so that we sort of set it up. Okay, all right. So I'm going to choose a different color. Okay, and I'm going to tell you this. Okay, look, I have some vector. Okay, I have some vector which is some w vector, right? I mean, which is aligned in the direction. Okay, and then what I also have is that some unknown vector u. Okay, all right. So what do I do? Probably I have to design the width in such a way that the positive and negative samples are separated with a maximum discrimination. This is the problem, right? Okay, so the question is, this unknown u is your test data. Okay, all right, and you ask the question that where does this, that's the question that you ask, right? Okay, so I mean, and how do I answer that? I mean, so typically what happens is, I mean, we do certain basic assumptions, which is, one of the assumption is we consider w to be orthogonal to the plane, right? Okay, all right, and also you realize that these planes, right, these planes are the decision boundary, right? And then also what we also do is that we project u in a direction orthogonal to w, right? Okay, so project u in the same direction as w, so that it's also orthogonal to the decision boundary, right? Okay, okay. You could, I mean, these are weight vectors, right? And so there could be a bunch of them, right? I mean, there are a bunch of weight vectors, right? Okay. So the question is, now in what manner should I project this? Okay, so what I need to do is, I mean, look, the problem is, I mean, if I have an unknown u, I mean, I really don't want this guy to fall here. This is what I don't want. I mean, in order to be able to achieve that, I need to make the projection in such a way that it either falls on this side, okay, maybe the negative training examples, and or the other side, which is the positive training examples. Okay, all right. So therefore, let's say that this guy, this width is like, there is some lower threshold, right? And since you are projecting u in the same direction as w, so what you are looking at is the inner product of u and w, right? Okay, so let's do that. So let's write the inner product of u and w. And what can we say about this inner product? This inner product, so that u does not fall here within these two support vectors, the inner product has to satisfy some lower bound, right? Okay, so it has to be greater than or equal to some lower bound. So some lower bound threshold, okay? And without loss of generality, I mean, this is just so that we are consistent without loss of generality. If I assume b equal to minus c, I can write this as this. Okay, all right. You can easily check this. I can write this at this. Okay. So the idea is, this is one decision rule that I obtain. Okay. This is one decision rule that I obtain. Okay. And let's say, let's give it some number. Okay. And the unknowns are w and b. Because, you know, there are a bunch of w's that we don't know, and then there could be some unknown bias, correct? Okay, all right. But the whole point is, we want to compute these w's, right? I mean, so, I mean, at this point of time, we are in no position, I mean, we are in no position to compute the w and b. So we need to lay additional constraints such that we are in a position to compute the w and b. So this is what the problem is. Okay, so let's, you know, do that. So we sort of set the problem in such a way that, you know, we set up some distance, some sort of distance, and this is just a mathematical convenience, right? Okay, so there are, because you remember, this is the same, the u, and so there could be u plus positive training examples, and there could be u minus negative training examples, and they should be actually separated by this width, right? And we are taking this inner product of w and u. So we take some positive training examples, right? We also take the negative training examples, the inner product of w and the negative training examples. And if you recall the decision rule from the previous slide, the decision rule was the inner product of u and w plus b greater than equal to 0, if you recall. Okay, so this u is unknown, right? I mean, this u could be anything. This u could be a positive training example, could be a negative training example. The question is, irrespective of whether this u is a positive or a negative training example, this condition has to be satisfied. Okay, all right. So let's do this. Let's say I set an additional condition that instead of just saying this is greater than equal to 0, right? Because greater than equal to 0 means what? I mean, you are kind of expecting a line, right? I mean, and you are expecting the inner product uw plus b to be just above 0, right? Or below 0, right? Instead of that, I mean, we really want two support vectors, correct? So we kind of say that, okay, let's assume that this guy is greater than or equal to plus 1, and when it comes to the negative training examples, this will be less than equal to minus 1. So what is going to happen? I'll have, let's say this is plus 1, let's say this is minus 1, so that at least, you know, there is this 0 line, correct? So it's on the either side of the 0 line. Okay. Now we do a lot of little smart maneuvers in order that the problem becomes more tractable. Okay, so what I do is introduce a characteristic variable yi such that for the positive training examples it's +1, okay, and for negative training examples it is -1. Okay, all right, and therefore if I multiply, I have two inequalities, right? If I multiply the first inequality with yi plus and I multiply the second inequality with yi minus, either way what I will obtain is that the yi plus times wu plus b greater than or equal to 1, nothing will change. But however, in the second equation, inequality, if I multiply this by yi minus, because yi minus equal to -1, the -1 and -1 makes it a plus, and all right, and then you would have so irrespective of, so what I wanted was, it's sort of an uniform decision rule for both positive and negative training examples, right? So by introducing a characteristic variable yi, I am able to accomplish that. So it's sort of, I have a uniform decision rule now, okay, all right. And what I don't want is this, okay. So in other words, if I just use some random training example values for u, right? Okay, I can rewrite this as yi wxi plus b -1 equal to 0. Now if your training example xi, so it is like for training example xi satisfies this equation, that means it neither belongs to a positive training example nor a negative training example, right? Okay, and it just falls here. Okay, all right. So therefore, the question is, if you recall, we began asking that question, that how do I quantify the width, right? So what is the width of this? What is the width that we are trying to maximize, right? Okay, so let's look at that problem carefully. Okay, so here is the deal, right? I have this guy. What I want is, I have a projection, right? Typically speaking, I at least need this much. Okay, I at least need to cross this much so that I can label examples as positive training examples. So this is x plus, and this is my limit for calling examples as negative training examples, because that's what we decided, right? Okay, and then I just complete the triangle, right? And if you complete the triangle, you just have an x plus minus x minus. Okay, so far so good. This is just comes from a vector addition, right? Okay, but what you do here is that you have to have the minimum distance between the, there are multiple ways you can measure the width, right? But in order to measure the least distance between these two supporting hyperplanes, you would have to take, draw a unit normal, right? You have to have a unit normal. So what is a unit normal? How do I get the unit normal? So the unit normal is nothing but the inner product of what you have, right? Inner product of what you have with, if you recall the weight vector, right? Remember the weight vector when we talked about the weight vector. The weight vector is actually in a direction orthogonal to the decision boundary, right? So w divided by the length of w will be a unit normal in that direction. Okay, and what we wanted was, remember, you wanted u, okay, to project in the same direction as w, right? So therefore it's like sort of a same direction or parallel, correct? Okay, so this guy is nothing but the unit vector. So this is nothing but the unit vector. Okay, all right. So now what we do is, if you really think about it, this is nothing but the width of the straight. isn't it? This is nothing but the width of the street. Okay, so this is the width that we are supposed to optimize. Okay, so this now boils down to an optimization problem. So I think, I mean, we need to write down somewhere something. Okay, we'll clear the canvas. Okay, so at least now what we know is, we know that the this is the width that we need to optimize. Okay, all right. So I'll just write this down again so that we don't forget, right? So SVM continued, right? I mean, just for our reference. So the width is, so this is something that we need to simplify, because I mean, this in itself is hard to compute. Okay. Okay. So how do we simplify this? Well, we know, we know that, I mean, we don't want examples to fall between the support vectors, right? I mean, and between the support vector means, I mean, there is this, relationship that we built in, saying that there is this, one support vector which is 1 and the other support vector which is -1, and then you have positive trainings examples which will cross the +1 threshold, and the negative training examples which will fall below that -1 threshold, right? In between there is 0, and this is exactly the region where we don't want our examples to fall, correct? Okay, so I mean, let's say, just consider this, yi is a positive sample, let's say. Okay, let's say yi is a positive sample. Okay, all right, and then your yi, you have this condition yi, which is the inner product. Now when this, what is this yi? If you recall, this yi is nothing but a characteristic variable, remember? This yi is a characteristic variable which could either take a +1 value or a -1 value, if you recall, right? When it takes a +1 value, right, the inner product xi w, right, I mean, this will be a positive training example or positive sample, right? Okay, however, when it's -1, it will be a negative sample. That's what the deal is, I mean, right? Okay, so therefore, I mean, if I use yi as +1, so if I use yi, because it's a positive sample, as +1, right? Okay, then what this means is, you have an xiu, right? Because this yi is just a +1, xiu plus b -1 equal to 0, right? From this example, or in other words, you have xiu equal to 1 minus b. Okay. Similarly, I mean, when you use yi as -1, so when you use yi as -1, the same inner product, right? The same inner product, so it would be a negative training example. Okay, so you multiply this by a -1, and then what you got is, so this is u plus and this is u minus. You multiply this by -1, right? So there is a minus sign in front, correct? Minus b -1 equal to 0, right? And what that implies is, I mean, if I plug in, transpose this guy to the other side, I have xi u being a general representation of both positive and negative training examples, and this will be 1 plus b. Okay, all right. So I mean, having said that, so basically this is what I want. Remember, I mean, so please don't forget, Oh, by the way, I made a mistake here. Sorry. So this is like your training examples are, your positives and negatives should be here, not here, right? Okay. Now remember, this is what we are trying to compute. Okay, the width of the street. So what is the width of the street now? X plus minus x minus and w over norm of w, right? So do I know what this x plus mu? Yes, I think I do, right? I mean, it's pretty straightforward. It's 2. Just simply add. Okay. Therefore, the width of the street is nothing but 2 over norm of w. Okay. All right. I mean, you can use anything in place of u here. So I mean, if you use w, we can easily see what happens, right? Okay. Okay. So therefore, I mean, I finally sort of have an optimization problem going my way, which says you maximize this. Okay. All right. Okay. All right. Maximize this, and subject to the constraints, subject to the condition that yi wi x plus b minus 1 equal to 0, and you are dealing with unit vectors, so norm of w equal to 1. So this is your optimization problem, I mean, as far as support vector machine is considered. Okay. Now the question is this a solvable optimization problem? I mean, can I solve this? Well, I mean, it turns out that this thing is notoriously hard to solve, okay, because of the structure of the problem, and it's actually a non-convex problem. Okay, we would like to discuss more about this. We would like to discuss more about this particular condition and what it implies. Okay, but that's for the next lecture.